All right, the goal for today is to get you kind of a little bit more familiar with intermediate 2D kinematics. The way I separate it, by the way, if you didn't already have this figured out, there is no actual separation in real physics between simple, intermediate, and advanced. I do that on our homework specifically to try to give you a gauge of what you need to be focusing on. Like if you know you're struggling with simple 2D kinematics, obviously that's where you should try to live until excuse me, until you have that entirely figured out. The main separation I would say right now is simply this. If I launch an object horizontally, that's for the most part, I would say that's a simple problem. Now, that being said, there was some stuff I asked yesterday, like how fast the object hits the ground, that I would argue is in fact a little bit more complex. So you are going to see in the intermediate kinematic problems also problems that start horizontally. You don't have to think anything weird if that's the case. That being said, when we left our intrepid heroes yesterday, we were starting to launch things up in the air at an angle. And what I was really trying hard to get you to see is that you should not look at this as one arrow. You should look at this as two arrows. And those arrows, this guy right up here, the hypotenuse, would be something like your velocity initial. It could be something like 30 meters per second at 30 degrees, okay? What is this bottom part of the triangle? Like if we had to give it a variable then. The bottom part of the triangle right down here, what does that visually represent?
Initial x.
I'm going to say it a little bit differently. I'm just going to say x, velocity x. Why am I not using initial? Now, if you did decide to put initial x, there's zero problem with that whatsoever. You just have to make sure to not accidentally confuse yourself that it might change in that particular case. But that being said, what is the other side of that going to look like? Initial y, correct. Now, just as a heads up for what you're about to see in just a second on a video, you might remember that where you place a vector doesn't inherently change that vector. Meaning, if I draw this arrow and that arrow, those are equal to each other because they are the same size and point at the same direction. So there is another way to draw this, which you're going to see in a few moments, and that is that this is velocity x and that this is velocity initial in the y. Those two triangles mean the exact same thing. The right triangle in this case might make it a little bit more obvious what's happening. The left triangle is nice because you can clearly see the trig that would get you each of those particular pieces. So we'll talk about both particular methods throughout. Just want you to know if you see one versus the other, they're essentially the same type of thing. All right, let me ask you some quick questions, okay, that pertain maybe to last chapter even a little bit. Let's say this is our initial velocity. Let me call it here. I'll throw this guy right up over here. We'll just use that one on the left, okay? How do you know when an object launched in a projectile is at the top of its path? So I throw a object in a projectile. Let me rephrase that. Last chapter, I would have done this. How do you know when an object going straight up and down is at the top of its path?
When it's vertical velocity, when its velocity is zero.
When its velocity is zero. Now, we would have said velocity final is zero, but yes. But you've already just answered the previous question. So how do you know when an object in projectile motion is at the top of its path?
It's actually changes.
Oh, careful. I think you said the wrong one. Its
Its
y value is
Zero.
zero. Correct. You might say velocity final in the y is zero. That being said, visually, not maybe numerically, but visually, you should be able to answer this question. Okay? How fast, then, will that object be going at the top? Let me ask you a different question that might be easier.
Velocity x.
There is what I was looking for, yes. The question I was going to ask, in case you struggled with that, is which direction is it headed in at the top? Well, if it's not moving in the y, which way is it going at the very top? If it's not moving in the y,
Right or left?
right or left. So in this case, it would be going right. So if you really wanted, at 0 degrees or horizontally, okay? But what do we know about the velocity in the x the entire time? It stays the same. So what is the velocity at the very top of its path? The velocity in the x. Now, I talked about that in terms of words and concepts, but here's a great video that I feel like is meant to do the work of like what is happening to the velocity components while we travel along. By the way, these videos, I have them linked on, I think, both sets of assignments. They're not going to help you necessarily do the problems, but they might conceptually kind of help you in this understanding. This second video right here, we're not going to show it in class, but in case you're interested, Mythbusters actually did do the whole bullet fired, bullet dropped conversation to see which one hit first, and of course they find what physics definitely would expect, and that is that 100%, even fired at full bullet speeds, they do hit the ground at exactly the same time. Now, this video that I'm about to show is about 26 seconds long and does a great job of just kind of visually showing you what's happening to each component in when it's in motion. Why is it slow-mo? I don't know what the deal is here. Hold on, let's refresh. Internet's being rough on us. Let's try again. This time a little bit more legato, please. With more feeling. Still not very smooth. I don't know what to do. All right. Oh, stop. So the orange arrow right there. See if I can actually get it to go where it's supposed to go. Stop right there. That represents what? That's initial velocity. The best thing to understand about the hypotenuse is the hypotenuse is in control of nothing. The hypotenuse is a direct result of what's happening in the x and what's happening in the y. So the better way to think of it, like we talked about yesterday, is looking at its components. And there, like I said a second ago, there you see the components of y and x written a little bit differently. So, which of these components do you expect to change? Expect Vy. Sorry, let me say that differently. Which arrows do you expect to change? So Vy is going to change. And V. But V changes as a result of what Vy is doing. Why does Vx not change? Why does it stay constant?
There's no acceleration.
There's what I'm looking for. The acceleration in the x is 0. If there had been acceleration in the x, would it stay constant? If there was a wind blowing to the right, would it stay constant? Absolutely not. It would speed up in the x. But right now, we're assuming there's no acceleration in the x. So, similar question. Why does the velocity in the y change then? Yeah, so how much is it changing? It is changing about negative 9.8 every second. So negative 9.8 meters per second squared. So what does that mean Vy is going to do then? Less. No, not quite what I'm looking for. Sort of half the time. You're right. What's that?
Lower magnitude.
No, that's I'm not looking for a synonym of less.
Go down.
Closer is to what I'm looking for. Okay, what I'm trying to get you to notice is that acceleration being negative doesn't mean it's going to get less or bigger. It's just that conversation from last chapter. It's going to change in the negative direction. So for the first half, you are right. Come on, are you actually going to do it? There it is. Notice, by the way, pausing at the top real quick, if I can do that, because it's a stupid video right now. Notice that that picture right there is what I was trying to show you a second ago. If the velocity y component is 0, then the velocity is just the velocity in the x at that particular time. But the back half of this, of course, the velocity y is changing down because of gravity, and v is changing correspondingly. So the overall velocity is really controlled by its components, and of its components, only one of them is particularly changing. How are we doing with that? All right. Let's go on to some problems for today then. Let's get rid of this crappy slow moving video here. Oh, I know what it is. It's because I'm recording right now. The processor on this thing ain't great. Apologies, people online. You can watch the video though. It's linked on the website. All right, so let's go back to this. Let's say I've got a ball and I launch that ball at 30 meters per second at 30 degrees above the horizontal. So again, this is 30 meters per second at 30 degrees. Okay? This is that time I told you we would do yesterday, so if people aren't here today, sadly they're not going to get a vote in this particular matter. You get to decide how we present the information in class the rest of the time. Here were your two choices. We'll go x, y, vi, vf, a, delta t, and delta s. Kind of sort of, not that you have to put these boxes, but I'm going to put them right now so you get a general sense of what it is. Oop, I missed a box. Okay, or you can do this. Vx, VIY, VFY, A, delta T, delta X, and delta Y. Not to side you one way or the other, but I'm going to a little bit because I would like to stay consistent if I can help it. Last hour chose this one. Okay, don't care which, but it's totally up to you. Once again, if you see which way we decide to do this, and you're like, yeah, I don't want to do that, I want to do the other way, you are welcome to do whichever way is easiest for you, or honestly, even a combination therein, or something else that you find online, whatever. This is just deciding how I regularly present the information in class. So we're going to vote left or right. Which one would you prefer me do moving forward? Okay, how many of you would prefer the left, right? Cool beans, I can stay consistent. All right, since I didn't say anybody do left, does anybody want left long term? Because I will show both to begin with if you want, but I'm not going to do, I'll show you both to begin with, but I'm not going to long term do this. Okay, so where does, I didn't move it enough. Hold on, let's move this barely. Let's go, hold on, down, there, move over, because I couldn't fit everything on the screen. There we are, here we are. Now, all right. Where does 30 meters per second at 30 degrees go in either one of these? Nowhere. Correct. It doesn't. It doesn't at all. What do you have to do before you can start to fill in?
Find the components.
You have to find the components. And how are you going to find the components? Trigonometry. So here's your triangle. This is velocity in the x. This is velocity initial in the y. How do we calculate velocity in the x? You got this. Come on.
30 cosine 30.
Yeah. 30 meters per second. Make sure to put units on that. Cosine of 30 degrees. And velocity initial in the y is going to be 30 meters per second. Sine of 30 degrees. Go ahead and calculate those for me real quick. Let's just go with 26 then, just to be simple. Okay, 26 meters per second x hat. All right, let's start with that one. Where does that one go now? Okay, so if you're on the right side, sorry, this should be x. It's confusing. If you are on the right side, you are just filling it in right here. This is 26 meters per second x hat. You do need to show the work somewhere on your page for this. If you're on the left side, this is 26 meters per second x hat there. And since it's a 30-degree triangle, you probably could have predicted that velocity initial in the y was 15. But if not, obviously punch that into your calculator, and you would get that this is 15 meters per second y hat, and this is 15 meters per second y hat. All right, what else do we know? So if you're on the right side, you can just put negative g in that case. If you're on the left side, you would put negative g, but you would also put that this is 0 meters per second squared x hat. Now, I reminded you yesterday, and I'll remind you again, there is a problem on the intermediate kinematics in which gravity does in fact go down and to the left. So you don't get this nice distribution in this case, and of course you will find that just with trig, the same way that we did here. But for people over here, just as a heads up, when that happens, you're going to want to add the following. This is now AY, and you're going to want to add AX in that particular case as well. But that's not what we're doing right now. Beep, beep. Go back. There we go. Okay. Now, the information that I've given you is pretty much all I've given you so far. Is that I'll tell you one more thing. Let's do this. Let's go that the object in question, the ball, is 1 meter in the air. Where does that go on our chart?
Delta y. Well, negative y.
It doesn't. It does not. I haven't asked any questions yet. We don't know quite what we're looking for. 1 meter just says it starts 1 meter above the ground. Now, delta y might be right, but again, it 100% depends on what I ask. Now, this brings me to this. Here's what you have to understand about projectile motion, which I learned the hard way about 3 years into teaching when I went to another teacher's birthday party. It was down at the Sky Zone or whatever, the one with the trampolines and the dodgeball. It was a lot of fun. And I went there and I thought we were going to have a bunch of I was going to do flips like the Matrix or whatever, and I was out of shape. And so I bounced from one side of the trampoline to the other, and I was out of breath, which is what really happened. Now, that's not the point. The point of that is this. As a human on Earth, in this stuff, you really just get to decide one thing. And that's this initial thing right here. After that, that's it. A path is decided. There is a parabola with which you absolutely will travel through. Okay? There is no pressing the back button like in video games and controlling yourself in the middle of the air. So, for example, if you were throwing some numbers out there, a 27-year-old, and you decided to jump into the air at a particular velocity, okay, at a particular angle, your path is set, regardless of how many 4-year-olds are at the end of that particular path. Now, you might be up in the middle of the air and cursing in the middle of your head because after about 2 or 3 seconds' time, your position will intersect with their particular position, and their parents are probably not going to understand because you're a 27-year-old male and you collide in this particular case with that particular child. You don't get to control it once you're up there. It's going to happen. Hypothetically. Okay, this is a hypothetical scenario in which you are a 27-year-old man that is at another teacher's birthday party. You happen to be jumping around. You happen to not be looking where you're going. You happen to give yourself initial velocity and turn to see that there is, in fact, a child at the very end of that velocity. And there has to be a whole conversation between you and their parents because you're 27-year-old and you should be responsible at this point. All right, it's fine. It's fine. Hypothetically. All right, point is, in the more real sense of this, what this does for us in understanding why is simply this. Once this initial velocity is set, because you can't control gravity, right? If you could, that obviously would be an entirely different story. But since this is set too, right? Initial velocity, initial acceleration decide the path. After that, you can essentially ask a question of the math, depending on what you want to know. So let's start doing that, and let's talk about what homework questions would say here. So like a homework question might say, a ball 1 meter in the air is fired at 30 meters per second at 30 degrees. Where is it in 2 seconds? Okay, so that seems relatively easy. If I want to put in my information, how do I ask that question of the math? I just punch in 2 seconds here. Now I said, where is it? Which is a question of position. What are you going to go try to find now? Yeah, and technically, by the way, there are 2 answers here because there are 2 answers here. You do want both of them. So let's give you guys a head start. It's going to take about 30 seconds and see if you can't answer as much of that as possible. I'm going to be on along very quickly thereafter, but I'm going to go through this work pretty darn fast. So see if you can't calculate where is the object in 2 seconds. Hypothetically. Totally didn't happen. It did happen to you. Hypothetically. No one else. That being said, when someone does jump and the older person next to my 4-year-old, I definitely I feel what that parent felt. I understand. They were right. I was wrong. But... All right, what equation should I use for the x? I disagree with you. Not for the x, you shouldn't. Change in x is equal to? Almost. You're missing something from this. Vx delta t. This will be really quick math because, of course, Vx is just what? 26 meters per second x hat times 2 seconds will give me 52 meters x hat. So is 52 meters x hat the correct position in the x? Based on the fact that Spainower asked that question, I want to say no, but I feel like the answer is just go with what. Yes, it's correct. Yes, it is 52. Now, what should I do for the y direction?
Delta y equals velocity of initial y del t plus 1.2 a of y times.
And plugging stuff in here because it's relatively plug and chug. What is velocity initial in the y? 15 meters a second y hat times 2 seconds plus 1/2 times negative g times 2 seconds squared. And if I'm not mistaken, you end up at 10.4 meters y hat. I didn't do that in my head. I remember it from last hour. So is 10.4 meters y hat the correct answer?
No.
No, it is not. Why is 10.4 meters y hat not the final position? Because you started a meter above the ground. So the final position should be what? The final position, the final answer that you would write, this is how I would write it if I said where is it, you would write it is 52 meters x hat plus 11.4 meters y hat. That looks like a complicated math, so let's talk about what you're actually doing there. Here's a ball. Here's the ball being fired, obviously not to scale. It's going to make some projectile right here. Basically, we know that it is 52 meters along the x and 11 meters along the y. Now let me ask you arguably a hard question, but it's meant to be relatively easy based on these numbers that we have calculated as well as our starting numbers. At this time, is the ball going up or down? I'm going to calculate delta y as being 10, positive 10, right? Doesn't that mean it's going up? Not necessarily. Not inherently either. When is it going to be at its peak?
When the Fy is 0.
0. Do you know when that is?
No.
Actually, arguably you do, but we'll come back to that in just a second. Let's start with this. Which value in your setup should you calculate in order to answer my question, is the object going up or down? Velocity final y, yes. And if it's positive, obviously it would tell you up. If it's negative, it's going down. But actually, there is an easier question. This next question can absolutely be answered without doing any math, given that you have this, and totally will come up on a multiple choice test. In this setup, how fast does it take to get to the top? Don't grab a calculator. And if you grab the if you don't grab a calculator, that means what do you assume about g?
10.
It's 10. So I'm asking, how long should this object take to get to the top? 1.5 seconds. How did you quickly just do that? Well, yes, but come on now. Okay, why did you do that?
Because gravity changes the
There it is.
VIY in the
By 10 every second. So mathematically, yes, the mathematical is 15 divided by 10. But probably a better way to understand this is answering this question. How fast will the ball be going in the y after 1 second? 5. You should know that it changes in the y by 10 every second, so it takes 1.5 seconds to change by 15 is essentially what's going on there. Okay, now, so that being said, is this object going up or down?
oh down.
Then it's going down. There it is, because it's past that 1.5 seconds. Other quick question that you should be able to answer based on the very first question that I asked today. How fast is this object going at the top of its path? Obviously, we're not looking at the top of its path. 2 seconds is beyond that, but you can still answer this question if you know where to look. It's 26 meters a second, correct. Because how fast would it be going in the y? 0. And so we would only be traveling in the x, and this goes right back to the very first thing we did today, right here. How fast should it be going at the top? Whatever velocity in the x actually is. Okay, let's ask a different question. We got 2 more things. I already have 3 more things, so we got to hustle up here. Okay. New question is this that I want you to try to do. How fast is the ball going after 2 seconds? Now, because I still use the 2 seconds thing, I really don't need to change my set of variables. I can keep that exactly the same. I'm just looking elsewhere. how fast is it going after 2 seconds is exactly the type of problem I gave you yesterday when I said how fast does that car hit the ground. So I want to try to give you once again about a minute and a half head start on this. See if you can't calculate the answer to this question without me. If you can't, I'll give you some help in just a few seconds. How fast is this ball going at 2 seconds? Okay, we'll stop it. I hear students say that. Don't you think I also, at the end of the day, because you guys are doing physics for the first time. This is my 5th time. And one of those was freaking physics 2, in which we were discussing electric field and potential difference and the energy and all this stuff all wrapped up into like 9 more layers. I'm tired too. Suck it up, autograph. Sorry, that wasn't nice. I don't really care. I do care. Sorry, I'm the next bag. I both do care, but also you should suck it up.
Do you preach your recording half the time?
What's that?
Do you preach your recording half the time? Or you just...
Oh, my voice preach during my recording? Sometimes. I don't know what happens. They'll wait. They're not paying attention to me right now online. Right now, they're doing the problem just like I asked you to do. How fast is this going after 2 seconds? What are you going to find right now?
VFY, and then you're comparing it to VX.
So let me show you a visual in case any of you are stuck. And if you're not stuck, don't pay attention to me right now. This is how fast you started, Vx, and velocity initial in the y. And of course, the first thing we did is we split it into these components using trig. Yes? We've just learned that the ball is now probably somewhere like right here because it's past the top. So it should be going this way. Now you'll notice in the last answer I gave, this guy, I didn't make you put it back into polar. I let you leave it in the x and the y. Why? Because nobody usually cares that the delta S is right here. All they care about is how far to go in the x, how far to go in the y. That being said, when I look at this triangle right here, if somebody ever asks me how fast an object is going, do you think they care about the x or the y? No, they want the hypotenuse. That being said, can you calculate the hypotenuse without the x and the y? No. Which of the two do you already have? You already know the x, so the first thing that you should do is calculate the y, and then do trig to answer the actual question, how fast is it going? That would be your hypotenuse. So firstly, go find VFY, and then use the trig to get that. I'll give you another 30 seconds to get out in front of me and do this. Correct answer is 26.4. Here we go. So to calculate what it is in the y, I just used the equation right up here at the top. I used VFY equals VIY plus acceleration times time. So that would be 15 plus the negative g times t, aka what this equation is doing is it's going to say, hey, it's going to change by about negative 20. Technically negative 19.6 if you take 9.8 times 2. Since I started 15, 15 plus the change of negative 19.6 gives me, it's going to be going negative 4.6, which is why it's going down. This is the proof that in fact, yes, it is going down at this particular time. But this is 26, this is negative 4.6, so does the ball land at negative 4.6 meters per second? In the y it does. It's also going in the x, 26. So we have to combine them together, and the only way to combine them together is Pythagorean theorem. And after you do Pythagorean theorem, since 26 is so much freaking bigger than negative 4.6, it kind of makes sense that I'm not that much different. It's also not that far past the beginning. So yeah, it's mostly 26 meters per second within that spot. How are we doing? Fist to 5, your abilities to recreate this. Cool beans, let's make it different. Okay, we're gonna go back to the beginning here, but we're just gonna ask, I said at the beginning we were asking questions. We asked two different questions. The first question is, where is it? To get where is it, we calculated these two things, and of course we knew that we had to add x in a couple of spots. The second question is, how fast is it going? Which is really a combination of these two things. Notice I'm emptying an empty spot, but that's because velocity in the x initial is also, velocity in the final y. And combined them together to get our 26.4. Let's ask about the same scenario, but I'm going to ask a different question. The question is, where does it hit the ground? So this is very similar, going back to the very first problem was, where does the thumb hit the ground? Okay, let's talk about what should stay the same here and what should be different. Should I start with the exact same velocity in the x and same velocity initial in the y if it's the same ball, the same scenario and everything? Yes. Should acceleration still be negative g? Yes. Should time still be 2 seconds? No. At a different location, it's going to take longer or shorter to get there. I don't know what time is. So what do I do mathematically to ask the question, where does this hit the ground?
Solve for delta x, but plug in negative 1 for delta y.
There it is. Basically, you kind of, to simplify that, to ask the question, when does it hit the ground, I'm going to set delta y as negative 1 meter. Why did we use negative 1 meter? Because it started 1 meter above the ground. Right? Now, notice I said at the very beginning this 1 meter doesn't go anywhere. And Elia says, oh, it could go in delta y. And I said, not inherently, because it depends on what's being asked. As a matter of fact, arguably, this 1 meter is also still not in the setup. What's in the setup is this. If you go back to this picture that I drew, now the second scenario is no longer ending here, which is after 2 seconds. It's ending over here. So this is the delta y, which is why we know it's negative 1. This one very much is a exact same scenario as before. I'm going to skip this a little bit because I'm going to point out something real fast and we're running out of time and I want to make sure to get this last problem. To find this, what you would probably do to get time is you would actually once again use this equation. What's your problem going to be?
Quadratic.
It's going to be a quadratic. Okay? You have to get good at this. To let you guys know ahead of time, the quadratic, actually, no, we used negative 2 last hour, so I don't know what the answer is off the top of my head. But I can tell you what it's close to. I can tell you it's pretty darn close to about, well, if it takes 1.5 seconds to go up in the air, how long is it probably going to take to come back down to the same height? 1.5 seconds. Technically, it's a little bit more than that because I'm divided by 9.8, not by 10. It's going to be a little bit more than 3 if you've done it correctly. 3.1 and change, somewhere in that particular range. Okay, and then of course you would just plug it into this equation, kind of going the opposite direction, to calculate instead of after 2 seconds, what is it? You'd calculate it after 3.1 seconds. What is it in that particular case? All right, last question of the day. When I was at a Cardinals game recently, actually not too recently, nobody goes to Cardinals games recently, but after about 2 or 3, I noticed they started doing a thing. When someone hits a home run, they actually tell you what the initial vector is of the velocity. They will say the ball was hit this fast at this particular angle. So I grabbed those two numbers and I wrote them down. In this particular case, we're going to say it's launched at 94.5 miles per hour. Stupid Americans and their miles per hour. And was launched at an angle of 22 degrees. And we're going to once again say that's from about a height of 1 meter. Now the ball, this is certainly not to scale, but the The ball has to travel 120 meters. And the wall, absolutely not to scale, we're going to say it's 3 meters tall. Now, it's not 3 meters tall. Busch Stadium probably is like 2.2. We're just going to keep the numbers nice and clean for you for right now. Now, if I want to set this up, what do we need to do first? Oh, I'm sorry, I got to ask a question first. Should probably ask the question before we continue on. Sometimes I forget to do that. So here's all this information. Here's the question. Does this person hit a home run? I did tweak some numbers because I just did tell you that I took the vectors from when they hit a home run, but I changed some of the numbers up here so you don't actually know. But that's the thing of it. I told you when there is a velocity and an angle that there is a path that is set. To go a little bit more to scale, it would be something like this. Okay, there's a velocity, and that velocity is going to cause a path. And whether or not that path is above the wall or below the wall, we don't know. I'm asking. Let's figure out where it's going to end up. So, what can we put into this particular setup to start asking the question, does this person get a home run? What do we need to do? Where does everything need to go? Tell me any of the given. Start filling in the chart. Anything in the chart. You got this. No, just tell me. What do we need to do? You can. I will do the math for you. Just tell me what needs to go up here.
Velocity x and velocity or initial velocity.
Now, before you do that, what should you probably do first? Before that, what should you do first?
Put the 120 in it.
No. We'll get to that in just a minute. You're trying to get velocity in the x and the y. What's the problem with doing that right now? You're in miles per hour. So the first thing that you should do is probably go 94 miles an hour. Okay, 2.25 miles an hour, 1 meter a second. All right, that's 42 meters per second. Now tell me what you guys were trying to do a second ago. How do you get the x? What's the trick? I'm your calculator. Punch it into the calculator.
42 cosine 22.
Yeah. So if you want to write that up here, by the way, you can if you leave yourself enough space. 42 cosine of 22, and of course over here is going to be 42 meters per second sine of 22. I'll ask for those answers in a second for any of you calculating. But let's see, what else do we need to put up here? Don't worry about finishing this right now. You're going to finish this tonight. The main thing is that we're trying to do the setup. Acceleration is negative g. Okay. I want to talk about what you don't do right now. I'm going to punch in what a lot of people might do incorrectly. They punch in that as 120. And what would they probably punch in for delta y? Not 3, 2. Why 2 and not 3? Because it started 1 meter above the ground, so the total change would need to be 2. But this is wrong, and this is going to mess you up, and here's the reason why. This says that I know the baseball will go 120 meters. And I know the baseball will change 2 meters in the air. Which basically says I know the ball will go through that location. Do you know that? If you don't know that, you can't place both of these. But what could you do instead? The question is, do we hit a home run? Can't place both. Now, there's 2 ways to do it. The first way is, yes, you could set 120. You'll notice you'll have enough information over here in the x that you could see how long it takes to get to the wall. And then with that time, you can figure out how much it goes up and down, and what would let you know that, yes, the person does, in fact, hit a home run.
It's greater
Greater than
3.
2. Greater than 2 would tell us they hit a home run. Asking a few questions here, okay? Don't go quite yet because I want to finish this off. What does it mean if you calculated a delta y of 0? It's possible. It's very possible.
It's only 1 meter up on the wall.
Correct. It means it hit on the wall 1 meter in the air. So what would you calculate delta y to be if it does hit like right here at the base?
-1.
You get -1. Now, does math know that this ground is in the way? No. So what would happen if you calculated delta y of -3? What would that technically mean?
It hit the ground.
It would say it would hit here, so we would just trace it back. In truth, it hit it earlier. And if you wanted to find out where, you'd set delta y at -1 and calculate x, and you'd find that x is definitely less than 120 in this particular case. There is one other way to do this, and while it is the harder way, I do want you to understand it, so don't wrap up too much yet. Here we go. The other way to potentially do this is this. Instead of setting 120, you could also set delta y at 2 meters. Now, the reason why that's going to be harder is that how many answers are you going to get for time? Why will you get 2 answers for time? Sure, but in real life, why will you get 2 answers for time? Because it will cross a delta y of 2 twice, so you would need to know in that case, understanding what that is, that you would use the larger one, and then you would calculate x. And obviously then, how would you know that you hit a home run? The answer is bigger than 120, correct. Now, definitely going back, the easier way is to plug that in at 120 and to calculate what this is. I don't know what the answer is, so listen to this carefully. I expect all of you guys to do this for tomorrow. Okay, now I don't need it to be correct, but tomorrow when you come in, I'm going to be grading for if you have done it or tried to do it versus if you have. I don't need it to be right. I do need all of you to try to have done it coming in tomorrow. By the way, don't forget that you guys are coming in here first thing tomorrow in the morning, so you're not going to have any other time. Make sure that you tried that. Yes.
We'll be on the stream or just doing watch the YouTube.
What do you?
I've been following you more than writing it down.
All right. Well, I'll give you the numbers then real quick. All you need. 94.5 miles per hour is how fast it was launched at 22 degrees, 1 meter in the air. The wall is 120 meters away and 3 meters up. Does he hit a home run?
Oh, yeah.
To answer that question, though, I will also put it on online as well. Bye-bye, people online.